Now filters. How to go about filtering in MATLAB. See, this is a very interesting example. So I have taken three sine signals: sine of n, sine of 10n, sine of cos of 5n, and the input is having combination of three sine waves. And I am going to do filtering now. You are going to see how the signals are getting filtered. And I am going to choose the rectangular pulse to be the impulse response of my system. And I am going to give y to be the convolution. You know, y is always convolution of h comma x. When you do convolution in time domain, you have to do the product in frequency domain. So I am doing product in frequency domain. You'll run this and see, you will be getting the same answer. Here, time domain and frequency domain. Time domain, you see h of n is a rectangular pulse, x of n and y of n. Frequency domain, h of f, x of f, and y of f. When you see the domain, you can say that both are not same, because definitely a signal will not be same in time domain and frequency domain, right? Both will be different. But the final end answer, whatever do by convolution or thing, the answer will be same. So if you plot, if you take f inverse f of t and plot, you will get the same answer for x, h, and y. So what I have taken here, I have taken input as sum of three sine wave signals. I have taken h to be rectangular pulse. So if I take h to be sync, see what is the output. See how the output is going to change. The sync function. So output will change. And don't say from these two diagrams, you don't come to conclusion that h, x, and y have to be same in both the domains. They will never be same, because one is time domain, another one is going to frequency domain. So now rectangular pulse, the another form of rectangular pulse I have taken, you can see the output will be different. Sync square function they have taken. You can see the output variation. And finally, we have two sync function. Get the answer. Okay, so this thing is in MATLAB. The only thing we have to vary the input waveforms and see what is the output. So now we are going to see how to filter an image. So we have seen digital image processing, right? So now we are going to see how to filter an image. I'm going to read an image. I'm going to convert the image into double, and I'm going to display the image. Okay. Now you see I'm going to split the image into RGB, and I'm going to apply a filter. I am just running that. See here, I'm taking a rose and bring a flower.jpg, and you see I have filtered that image using a 2D convolution filter. So same way how you do it for R, G, and B, and we using the corresponding R. For R, G, and B, I have to write the same code. Okay, you have to write the same code for R, G, and B, and I have to run. So I am just filtering the rose image, and I'm showing you the output. This is the original image, and this is the image after filtering. What filter I have used? Convolution filter, and I have used the convolution filter size is 5. Assume if I increase the size to be 15, see how the image is changing. You see the blurring happening. This is the original image. This is the filtered image. You see how much it is blurred. So I keep a 10. There is still blurring, but it is not that much amount of blurring. I keep at 5. We did not have blurring at 5, right? So we run and see what is the blurring at 5. Original image, somewhat blurring is there. This original image is very sharp and this image has blurring. So as you increase the kernel size, you can see the image getting blurred. This is actually signal processing because we are doing convolution. Everywhere, whatever signal or image you do, you cannot escape convolution. In a normal signal, we'll be doing convolution in a single dimension, but for image, we'll be doing convolution in 3 dimensions.